Good morning, everyone. Welcome to another Coffee Break webinar. My name is Fred Phillips. I'm an applications engineer with data physics. And we're going to be covering the stepped sine analyzer test type in the Data Physics 900 series software. The agenda today will cover stepped versus swept sine tests and when to use each, setting up and then running a stepped sine test. Swept sine tests are one of the oldest type of vibration tests, and they're still in common use today. They're a quick and easy way to expose the test article to excitation across a wide frequency band. But what happens when a test article has a strong resonance or other non-linearity in a particular frequency? When the sine sweep test only excites that frequency for a moment and then moves on. The test article isn't given time to absorb energy at that frequency, and the response may still be changing when the test has moved on. In this case, the real response of the test article is not captured with the sine sweep test. That's where the stepped sine comes in. Stepped sine tests break the continuous frequency band down into discrete frequency steps. For each step, there's a prescribed settling time to allow the test article response to stabilize, and then measurements are taken. While this takes more time to run, it gives more accurate response for highly resonant test articles. So let's set up a stepped sine test. Today I'm using an Abacus 901 to run a GW V4 shaker with a 30 watt amp, and my resonant test article is a 203 millimeter bicycle brake rotor. I'll start by opening a new test and select the step sine type. I'll name this one SSN Coffee Break, and I'll make sure that it's in my webinars project folder. The test tab is mostly for bookkeeping, and any of these fields are searchable across the test database from the Manage Test tab. I'll select my 203 millimeter rotor as my test article. And Channels tab is where I set up my inputs and define a range for my output. This test requires two inputs in order to generate transfer functions. I have two accels selected, so I'll select them both. Change the coupling to ICP. Oh, let me make sure. Yeah. Select my 901 instead of my Quattro. This will automatically change my inputs table and also gives me the ICP 4 milliamp option. For this test, I'll select a range of 3 volts for both channels. And I'll select the database sensor type. So I can then go in and select the serial number that I have on each channel. Channel 1 accel is almost collinear with the actuator, so I'll name this one actuator. Channel 2 is on the edge of the rotor, so I'll name this one edge. For more info on the searchable test database from the test tab and the channel table setup tricks, please see our YouTube page. Next, I'll verify that we have channel 6 selected as the output and select an appropriate range for my shaker. The step sine tab parameter subtab is where we'll do most of the test setup. The test is broken up into bands, and parameters for each band can be independently adjusted. The bands act as a run schedule, as they will be tested sequentially. Controls on the left allow you to add, insert, subtract, and move bands up and down the schedule. My rotor has a large resonance near 30 Hertz that I'll focus on, so I really only need one band for this test, and I can delete the second one. The estimated time to run the band is shown in the first column, and if you watch, you'll see this update automatically as we make changes. You can set a custom range for each of your channels, or in my case, I'm just going to default to what I set up in the channel table. So in the frequency resolution property, you can select the frequency band, which combined with the order of harmonics you're interested in, sets the measurement frequency. I want to look out to third order harmonics. And again, focus on that 30 Hertz resonance. So I'll go from 25 to 35 Hertz. You can also set the sweep rate to be linear or logarithmic. And this determines the resolution options that you have. For this test, I'll go with a linear sweep rate with a 1 Hertz resolution. Moving over to the filter submenu, we can select the settling time. For this test, I'll go with 5 seconds so that we can see what's happening while we run the test. But there are various units for the settling time. You can also select the filter properties on the right to be either a set number of averages, or you can go until you hit a minimum coherence value for a particular channel. Finally, in the control menu, I can select controlling off the drive or source, or one of the inputs or a math channel. For this test, I'll use input 1, the accelerometer right over the actuator, and set it to a nice low 0.1 G. If this were the source voltage, the control level would be in units of volts. In the signal subtab, we can see our input and output channels and define which of the inputs will be used as a reference for the transfer functions or a minimum coherence for the averaging. On the right, we can select the signals that we want calculated during the test. Even if they are not plotted during the test, they can still be accessed in the test review. I've chosen to look at higher order harmonics, so I'll add in the averaged harmonic spectrum and the total harmonic distortion. That about covers the setup. It's time to run. So before we fire up the test, I'm going to configure a few of these graphs. I'm going to add my edge excel to the time history plot and to the spectrum plot. Then the graph attributes, I'll select to show their channel names. I'll also add a new graph to display the total harmonic distortion. And copy the graph attributes so we see the channel names. In the TRF tab, we have plots set up for the coherence, magnitude plus phase transfer function, and averaged linear spectrum. The parameters tab lets you track how the test parameters change between the bands. Since we only have one band for this test, this page isn't going to be very exciting. When running multiple bands, they will show continuously on spectrum plots, and this page is a bit more useful. I'll add a new page here to display the harmonics that we've chosen to look at. And in the first plot, I'll add the second order harmonics, then make a second plot for the third order harmonics. Again, we'll show channel names and then copy the graph attributes to show them for all. So now we're ready to start the test. I'll hit initialize and power on my amplifier. We'll name this something meaningful, like 25 to 35 hertz. And give the ICP cells a minute to settle out. So we can watch on the left side as the test state changes from settling to sweeping and back again. So currently we're settling on 25 hertz. Then it'll start sweeping up to 26 hertz and settling on 26 hertz for another 5 seconds. You can see in the time history plot that the edge excel magnitude is a bit more than the center magnitude. And if we auto scale the linear spectrum, that confirms this. Now that the test is finished, I'll hit end, which will move me automatically to the review page. In the TRF tab, I'll double-click on the transfer function plot to full screen it. We can see the magnitude increase and the 180-degree phase shift associated with the resonant frequency at 30 Hz of this test article. In my harmonics tab, we can see that there are harmonics present, but based off of the magnitude, they're not significant. That concludes this coffee break webinar on the step sine test type. For more useful videos on the DP software and how to perform various tests and measurements, please see the Data Physics YouTube page. For more information about data physics test systems, as well as web support forums, please go to our website, dataphysics.com.